Hello everyone, my name is Octave and I'm going to be talking about the work that I've been doing alongside Sophie, Kaleba, Humphrey, Burchell and Stefan Marr, all from the University of Kent, about AST and bytecode interpreters in a meta-compilation context. So firstly, what is an interpreter in this context? We're talking about a programming language interpreter, so ways of implementing programming languages, and for our purposes we're going to define it as something that directly executes high-level operations. So the good thing about interpreters is that they're easy to implement since they're just a parser and execution loop, which means they have a low engineering and maintenance cost. The not so good and the trade-off you do with this simplicity is that they're relatively slow because there's no compilation to native code. Unless there was a way to do that, which is just-in-time compilation, which I'm sure many of you are really familiar with, but I'm briefly go over it just in case. It's about calling a compiler during the runtime, identifying valuable code sections, often functions via runtime profiling, determining what could be a valuable target, and compiling it so that later invocations of that code block, code bit, will be through native code. So if you have a function called many times, for example, here, do something, after 1,000 calls, you might say, hey, it might be worth actually compiling it, and then later invocations of that same function are going to be through native code. So meta-compilation, though, why might want it? Just-in-time compilers are notoriously hard to implement. Has anyone in this room worked on a just-in-time compiler before? Many of you have, I'm sure. Would you describe it as being easy? Yeah. Fuck. I'm going to assume you were lying because it plays more into my agenda. Because if you want to actually implement an efficient just-in-time compiler, you need to actually have good profiling, inlining, common side reflection elimination, all the classic just-in-time compiler optimizations and whatnot, which tends to be a lot of work. So meta-compilation instead combines an interpreter and the user program to generate native code at runtime. And you get a just-in-time compiler like this from the interpreter. You just write an interpreter, you provided a few annotations to inform the meta-compiler, here's how the JIT should actually work in practice, and the performance ends up being surprisingly good, as we'll come back to in a bit. So to briefly go over two meta-compilation approaches, the two main ones at the moment, if we have code like this, partial evaluation is going to be more about making it a more compact unit of code through aggressive inlining and removing the bits that aren't needed in the computation, while meta-tracing is going to be about recording a trace, so an actual path through the program, and compiling this instead. I don't have time to go much into detail, but this is a broad overview of two main ways you do meta-compilation right now. So that's all fine and good, but what kind of interpreter do we actually write? And so there are two main approaches, which are bytecode and abstract syntax tree. So if we have an operation y equals x times x, in a bytecode context, it might look something like this. You load the value of x, you load it again, you call the multiplication function with send in our bytecode set, and you store the results in the variable y. In an AST interpreter, we would have a series of nodes forming a tree, and you would do a post-order traversal to actually execute the behavior associated with each node. It's not like a visitor pattern or anything, it's every single node encapsulating its operation. Like you're going to go through variable read x at the bottom and read the value of x, then the other read x, they're going to go back to the multiplication primitive, which is going to multiply them, and finally the variable write will write to the variable of y. So each of these is an actual object. And just to elaborate quickly, we're talking about self-optimizing AST interpreters as well. Since we're in the context of dynamic languages, if we have a function like getAge, for example, we can't know for sure what type it actually returns. Could be a string for some very weird reason. So if we have an AST like this, it has to handle the generic case of being like, what type of variable am I actually going to read? But we can perform runtime profiling and actually find out, hey, getAge always returns an int, so x is always an int and y is always an int. Therefore, we can actually rewrite the tree to specialize on the end case. And this isn't a new idea, but this is how you actually make AST interpreters way more of a viable choice in practice. So now the question is, would you want to go for bytecode or for AST? So if you're running a bytecode interpreter, you're going to have a more compact representation, and it's going to use less memory. But AST is going to be less compact because it's a bunch of objects, but it's simpler to reason about. But what most people are actually interested in are memory usage and chiefly runtime performance. And in terms of performance, bytecode seems to be the clear winner. Like this is an extract from the Yarv paper, which says the current Ruby interpreter is slow, because it was an abstract syntax tree interpreter at the time. There's the book Crafting Interpreters by Robert Nystrom, which is excellent, and I recommend it, which is divided into two parts, running a slow AST interpreter for starters and running a fast bytecode interpreter afterwards. And in the middle of the book, it says a fundamental reason why the AST interpreter is insufficient, it's because it's too damn slow, because it's an AST interpreter. I also got feedback from some experts in the field that kindly confirmed that bytecode was the clear winner in this context. So all is doomed, theoretically, outside of the domain of meta-compilation anyway, and this is what I'm going to be talking about for the rest of this talk. So for our study, we worked with our runtime systems that use the language SOM, simple object machine, which is a minimal small talk, and has all the classic object-oriented features like inheritance, non-local returns, closures, etc. And we evaluated it on two systems. We have TruffleSum, which relies on Truffle, a Java framework with the interpreter compiled ahead of time to native codes, and that uses a partial evaluation approach, like we saw earlier, with the Graal compiler. And PySum, which works with RPython and compiles to C, and it's part of the PyPy project, and this time uses a meta-tracing approach. And for both of these, we have both an AST interpreter and a bytecode interpreter. And what we're interested in is, within the domain of partial evaluation and meta-tracing, how do both compare to one another? Because they're going to be sharing a lot of codes, but the main difference between them is going to be the program representation that we chose to use, either AST or bytecode. And we work within both a partial evaluation context and a meta-tracing context, because we don't want to tailor too heavily to one approach. We want this to be evaluated on all meta-compilation approaches actually used at the moment. So all results in terms of runtime performance, first interpreter performance, so not taking the JIT into account, so important for warmup and also when just-in-time compiled code gets de-optimized and falls back to the interpreter. Java JDK20 is the baseline, and every single data point is a benchmark run. We also included Node.js because it's another state-of-the-art runtime system, and the bar is the median runtime. So we're going to be sorting all our systems from the median, with lower being better. So that's for Java and Node.js. What about our runtime systems? And it turns out that our best performing interpreters seem to be AST interpreters, PySum AST and TruffleSum AST, with PySum bytecode being roughly equivalent to them in terms of interpreter performance, which is surprising, as once again we would expect bytecode to be way more efficient in this context. When it comes to actually peak performance, so with just-in-time compilation thrown into the mix, we have something like this with Node.js, again, being faster than our runtime systems, but TruffleSum AST not being that far behind with roughly 2.2x in terms of median. So the best peak performance in our system seems to come from an AST interpreter. And also is a testament to the benefits of meta-compilation, considering there's a lot more engineering effort than actually writing a JIT, and yet you get around 2x slowdown compared to JDK20, which is acceptable considering how fast it is, in my opinion, very valuable trade-off. Admittedly, PySum AST performs rather badly in terms of peak performance for reasons I do not have time to explain, but I likely due to recursive benchmarks skewing the result in one direction. There's also the idea of using the least memory possible, obviously, and for this we used RSS, so resident set size, to actually find out how much memory was needed in practice by each runtime systems. So again, lower is better, and for TruffleSum, with both interpreter and just-in-time compilation, in our case, TruffleSum AST actually seemed to use less memory, or rather had a lower RSS, which is surprising considering we argued that bytecode was far more compact and AST's lot less compact program representation. For PySum, we don't observe this, but the bytecode and AST seem to be roughly equivalent with no clear win for the bytecode interpreter. So again, surprising results considering the premise. We also tried to maximize the memory used by the program representation, trying to evaluate how much memory was needed by the program representation itself, AST or bytecode. And for this, we did two things. One, just loading a lot of code, so with no runtime profiling, not executing it at all, and once while executing it. And if we do this for troublesome, you can see that the blue bit is the code, and there's a major difference between bytecode and AST, with bytecode using a lot less memory, as one might expect. But what happens is that when you actually execute the code and the orange bit comes into account, all the profiling information actually evens out the difference somewhat, since the difference between the blue bits is far bigger than the difference between the blue and orange bits combined, since there's a lot of profiling done in both cases. So when the AST actually is executed, the difference in terms of memory usage can narrow. And bytecode is still the winner because it's still the more compact representation, but it's not winning by as much as one might expect. So discussion. Bytecode doesn't seem to be the superior approach to AST, or at least there's no evidence that bytecode is the clear winner in terms of runtime performance. Bytecode is still more memory efficient, but the difference narrows more than one might expect when runtime profiling is thrown into the mix, which is going to happen every time you actually run your program. This is a study only for meta-compilation system and not systems interpreters, so there are some optimizations we couldn't implement on our bytecode interpreters, like indirect threaded codes. We tried to implement top stack caching as well and didn't get major speedups that way, even slowdowns actually. And there's more in our paper, including warmup assessment and a comparison of various optimizations in both an AST and bytecode context. So in summary, meta-compilation is the idea of getting a free JIT compiler from an interpreter. We set out to check out, to assess whether bytecode was the superior approach to AST in this context, like the literature seemed to suggest. We found that this was not the case in terms of performance or memory. And therefore, we conclude that AST interpreters are viable for meta-compilation systems, and that there may be more room for more reliance on AST interpreters in the future in this context. Thank you.
Thank you. A bunch of time for questions. Do we have any?
So you used in your AST interpreters the rewriting technique to get type specialization. Did you have like an inline caching approach or something in the bytecode interpreter to also get type specialization?
The bytecode also has inline caching, yeah. And we use a technique called quickening to like replace the bytecode with more optimized bytecode at runtime as well.
And
it had a lower impact than the self-optimizing nature of ASTs. We explained that in the paper when we compare various optimizations. And quickening did lead to speedups, but they were actually not as big as you might think.
And that's what the profiling, there was a larger profiling bar for bytecode, and that was the inline caches and the quickening metadata?
It's all the profiling performed by the runtime system, so by or RPython in this context.
Okay. Okay, thank you.
Hello, great talk. My question is, how did you control for the quality of the interpreter, of the AST interpreter or the tree interpreter that you have written? So maybe in your study you've concluded that one is not strictly better than the other, but maybe I wrote the bytecode interpreter and you wrote the other interpreter, so my interpreter sucks and your interpreter is good. So how did you control for that?
Sorry, is this about that you can't prove that the AST interpreter didn't get like, isn't better than the bytecode interpreter because it received more effort? Or
yeah, so what are you controlling for when you're doing this analysis? So maybe the tree interpreter took more effort, or maybe it has some trick that the other one doesn't, whatever. Yeah. So what did you control for, is my question.
I mean, that's an inherent limitation of the study in that you have to trust us that we tried as best as possible to optimize them to the fullest. But in terms of actually proving that we couldn't have made them better, well, I'm not sure how we could have, if that answers your question. Like, we tried various optimizations that didn't actually work out.
But you put, like, hand-waving the same amount of effort in each interpreter, let's say.
Yeah, sure.
Okay. Thank you.
Yeah. So
I was wondering if you have thoughts about predictability of performance. In a bytecode interpreter, one would expect, speed to be kind of always the same, and that may be good, unless it's really slow.
So like warm-up performance, I suppose, if you're expecting things to vary in this context. Again, that was in the paper as well. I didn't mention it because the results was that there were no interesting results. We compared warm-up for AST and bytecode interpreters, and we found out that neither warmed up much faster than the other, if that answers your question.
Okay. You should probably, we have a bunch of time left. If there are no more questions, we'll just take a wait.
Thank you for your great talk. So I'm wondering how to profile more, so kind of like an memory inefficiency of bytecode interpreter. So the problem of RPython is that it's hard to profile or investigate the internal profiling mechanism around the memory consumption and so on. So do you have any suggestion for that?
Any solution for what? Sorry, I didn't understand.
Kind of like investigating how to kind of maybe so RPython stuff like so RPython meta-compilation stuff to investigate the memory consumption or other kind of stuff. Or do you have any insights for that?
Sorry, memory conception?
Memory consumption.
Sorry, I'm not sure I understand the question.
Oh, sorry. Let's talk later.
Well, yeah, absolutely.
Sorry.
Okay. Thank you, Octave.